my expectation from the audience is more like a popular science summary, so it's going to be easy to follow. So this is a very important topic because it involves everybody, no matter your branch, your education, because it's about environment and climate change. And we, as a computer science scientist, computer science researcher, what can we do? Something to solve it, some part of it at least, not everything. So it will be a case study of application of machine learning on marine ecology. So let's start. Yes. So first I'd like to emphasize, as we all know, how important are our oceans for us. So OECD estimates that around $1.5 trillion of revenue is generated from our oceans, which is something like 3% of world GDP. And it's going to be double of that in another 10 years or so. And in order to do so, we have to maintain our oceans clean and sustainable. And it also provides around 31 million jobs in direct employment. So are we doing enough to keep it clean? This is the current scenario in many parts of the world, maybe not in Europe so much as this. In the last few years, we have, due to the human pressures on the environment, due to our own exploitation, we have really put so much pressure, and a lot of pollution is affecting the marine ecology. And a lot of the fauna, the important vegetation that grows behind or beyond the waters is depleting slowly, which is affecting our trade and affecting the whole environment. So government has been trying to study this and trying to make an assessment tool to assess the status of the environment. And to do so, they measure some indicators like chlorophyll, transparency of water, and how much the sunlight can penetrate in the water, which shows the clarity. Also vegetation and fauna. So a lot of these things are difficult to measure, and some of them are not even tangible. So one of the things which is a proxy for all the other measurements is eelgrass, which is a kind of a benthic vegetation, which is long strands and sharp edges, which grows in the coastal marine system. So the idea is, if you find eelgrass beneath the surface of the water in a coast, then you are in a good position and you are happy. If you don't find it, then there's a problem. Okay. Yeah. So the common way to assess this kind of studies is through satellite images. So there are a lot of satellite images available, and scientists have been trying to figure out, like, segment those parts where there's eelgrass, there's no. But there's a problem with it is because of the cloud cover. So there are a lot of places, especially in Denmark, and you cannot see beneath the clouds, right? And which kind of affects the whole study. Another way of doing it is through underwater videos. So there are like scuba divers with cameras on their head and towed by a boat maybe. So they are recording everything that's going on beneath the surface of the water. And there's a domain expert who's watching those videos hours on hours and noting down, okay, at this point there's an eelgrass, at this point there's not an eelgrass. So it's a very laborious and tedious job to do. And so we, as a machine learner, AI experts, what can we do about it? So can we automate this process of eelgrass, giving a system which is robust to noise, and also giving a, how do you say, universal method of determining eelgrass, because domain experts' predictions may vary. I mean, if you and me are both a domain expert and we may not agree on the same frame or looking at the same video, so it is a very common thing. Okay, so having done the motivation, this is what the data looks like. Some snapshots of the videos. It's a bit difficult task because as a data scientist, you look for some features from the data. So grass is green, right? But apparently the environment changes the color and the objects appear very different. So it becomes a bit difficult task to apply the classical feature way of doing it. And also we have a lot of noisy objects in front of the camera, like the hand movements of the diver, there's a lot of wires coming out. So it becomes a bit challenging. So what are we doing about it? So we are using something like an edge detection way of looking at it. So what it does is, it's trying to find the change of a gradient from black to white, and it finds those connected regions and calls it a line. So it's a classic line segment detection algorithm in a linear time. And using that on the images, how does it look? Yes. So we expected that these are the two raw frames of the video. So in one of the frames you have a lot of grass, and another one is like no grass. And the output of the algorithm shows that there are a lot of lines detected in the frames with grass, and there are not so many lines on the without the grass. So using the number of lines as one of the features, maybe we can distinguish between the region of grass and no grass. And actually we plotted a histogram over there in which we plotted like the frames with the number of lines detected, and we could see it's a bimodal distribution, and we can put some kind of a decision boundary somewhere. So we calculated two features out of it, the number of lines and total length of lines. And we will be using this too shortly. If I plot a scatter plot, where number of lines is on the x-axis and total length of lines on the y-axis, the data looks like this. It is correlated because it comes from the same observations and same measurement. The idea is, can we put some kind of a boundary? So we did that. The boundary or the threshold for number of lines came to something like 260 lines. And we did the same for the length of lines, which came around 6,300. And anything above that, we call it as present illgrass. Anything below that, we call it as absent illgrass. And in a given area, we found how many frames are present, how many are absent, and we found a ratio to get the coverage. And we actually had a domain expert who actually manually labeled this data, and we tried to match his opinion with our algorithm. And you can see that it's not so bad. I mean, the area where there is no illgrass by the expert, as they say, the algorithm also detects completely absent, 0%. An area of high density like 95% or 80%, our algorithm also says around 90 to 80% something. So it gives a good motivation about this kind of feature that can be used for classifying grass from no grass region. But then the next question is, which feature is the best? Should we use individual features or can we use both? We found that both the features make the same mistakes, and it depends on the situation. We found that feature 2 is more sensitive to noise, and feature 1 has a tendency to underestimate. So can we combine them? So we actually found that this kind of a formula, like a convex combination, like a lambda, which varies from 0 to 1, times some constant. And it's an optimization problem. I mean, this lambda came out to be 0.68. And using that, we found the decision boundary, which is a bit kind of in between both this. And our prediction on the right-hand side shows it kind of gives a bit better result. And quickly moving on, but before it was still not completely autonomous, because a man has to choose, the researcher has to choose the threshold by himself, right? And this one is called a GMM, Gaussian mixture model. This will completely even do away with that part. It will choose its own boundaries and stuff. So here is the red one is the Gaussian mixture model's decision boundary. Anything below that is no grass, above that is grass. And with that, the prediction seems to be quite decent enough. And it also detects the rare mistakes from the expert. So in one of the areas, we found the expert labeled something as 0%, and our algorithm is giving a lot of high density region, like 198. So we manually looked into the frames, and we found that there are indeed illgrass. And we talked to the domain expert, and they actually admit that maybe there was a misjudgment from their side. So this is also quite robust to human error. And the future plans is to finally use the satellite images and point those points where we found grass and use it to extrapolate to unknown regions. And that's the whole goal. And now some cool demo. So this is how it looks in real time. So it's moving and the grass is being detected. There are also some text being detected on the boxes. So it measures the location, the height. It's completely an autonomous system. And this is where there's grass, and the point there's no grass looks something like this. Very less lines detected.
Thank you.
Questions? Who has a question?
I have a question. You almost already answered it. You gave us one example of where the expert admitted he or she had made a mistake. Did you actually, in detail, compare how valid the domain expert's assessment of eelgrass was, frame by frame?
Well, that has been a question for the last 6 months, because there are a lot of places where our prediction didn't match with the domain expert, which led us to trust his domain expertise in a way. But we are trying to make it an autonomous system where you don't need domain expert. So we give you the system, you run the algorithm, you find your own eelgrass. You don't need a domain expert to actually tell you. So that's the whole idea about making this autonomous. Yeah, please.
How's the process when you chose the two features?
Yeah.
I mean, did you choose them, or how did you figure out that these are the two that are most characteristic for each grass?
Well, we started with the colors first, because green color is for, that's what defines the grass. Then you saw that it didn't work out because the environment changes. Then we thought about maybe it has sharp edges because it's kind of long. Then we thought about using some kind of edge detection to detect those sharp edges. And it worked, apparently. That was the motivation. Yeah.
So when I think you call it lambda. When you choose your lambda value, did you divide your videos into two segments and choose it based on one and test it on the other?
No, this is an unsupervised problem. So what I mean by that is you don't have a label information. So it's all about you visually going into some frames and see if your algorithm makes a prediction. Is it match with your own opinion, if there's grass or no grass? Because then nobody has actually labeled each frame.
Right.
So there's just a video and you have to figure out what is grass and not grass.
Yes. All right. Yes. So, but still, in the end, you get a supervised prediction because you want to compare it when you are bragging that you're doing well, which you can do. You are also comparing to the expert.
Yeah, the domain expert is the supervision.
Yes, yes.
With that, yes.
We have a question?
Yeah, Kira.
So instead of just taking the number of lines or the total length, did you consider like the size of the lines? Individual, like I have a lot of long pieces here, I have a lot of short pieces. Did you try anything with that, like the quality of the lines, kind of?
I mean, we can do more about it. Yes, we can actually even individually see if there is one big grass making all the lines or not. But for the goal of purpose of just detecting grass, no grass, we didn't have to go that deep. Yeah, but we can do that. Yes.
It would be interesting to look at like a histogram of length and make a prediction based on that.
Yeah.
Some short feedback here. Thank you very much, Sayantan, for that. I'd highlight the way that you told the story here, where you gave the story of the general relevance of using machine learning to understand our marine environment better, marine ecology, and the way that you gradually took us down into the detail of your study. That worked very well. You had me with you all the way there. In addition to that, you used rhetorical questions very nicely. Several people have done that today. By that I mean a question like, so can we automate this process? That works very well. It's one really good way of guiding your audience through things. And the final thing, you included us by saying, can we do this, as the scientific community? And also you included us in your body language. You took a step into the room towards us as you were explaining things. And then you took a step back when you were looking at your slides. That interaction with us, the audience, and your slides worked very nicely. So, thank you.
Thank you.